cubed minus 15x squared. This thing, this polynomial, is a standalone unit. What you are looking for is what object or objects multiplied together, what terms can create this. The first method of factoring involves finding out if there is a greatest common factor. And there actually is a greatest common factor of this and this. Greatest common factor of 3 and 15, would you agree with me that it's 3? And greatest common factor of x cubed and x squared, would you agree with me that it's x squared? Okay. If you take that greatest common factor and divide it out, what is left is going to be x, looks like minus 5. Okay. To check yourself, 3x squared multiplied by x indeed does give us that first term in the polynomial. 3x squared times a negative 5, yes, that is 15x squared. Now, presumably, you found the greatest common factor, pulled it out, leaving you with this. Is there any greatest common factor other than 1 that can come out of 3x squared? No. Is there any greatest common factor other than 1 that can come out of both x and negative 5? No. Which means the factored form, factored completely, of 3x cubed minus 15x squared is 3x squared and x minus 5. Unlike your number 24, what I used earlier, there aren't going to be a bunch of factors. This is akin to prime factorization. You're getting down to the bare bones of the factors of this item here. Now, if it was, say, 3 terms, the same kind of question can be asked, greatest common factor. Maybe 3x to the 4th minus 12x cubed plus 24x squared. Ask yourself, what can be pulled out, largest, greatest common factor of these 3 components? 3x squared again. I didn't mean to do that, but I did. 3x squared. And once I've pulled 3x squared out, what is left within is x squared for the first position, negative 4x for the second position, and 8 for the last position. Are there any other common factors that can come out of all 3? Well, these 2 share an x, these 2 share a 4, but all 3 do not share anything. Now, there is a second question that we can ask ourselves, but you guys don't know that yet, so I'm going to quit right there. That is the end result.
We did this last year.
Yes, we did. We just are a lot more difficult this year. And in your book, example 1 has 2 examples that look just like that. Okay? So asking yourself if there's a greatest common factor, and then getting down to the point where both pieces are considered relatively prime to one another. In other words, this shares nothing but a 1, this shares nothing but a 1. That's the first step in factoring. The second step in factoring is to analyze the various patterns that exist. Okay, the first 2 patterns you're going to learn, or that you did learn already, is something called a perfect square trinomial. A perfect square trinomial is created when you take any binomial and square it. In other words, multiply it by itself. Okay? Take, for example, x plus 2. Let's take x plus 2 and let's square it. This is perfect square trinomial. This takes the pattern a plus b squared. Okay, a plus b squared. A and b just represent positions within the binomial. Okay, that's at the bottom of page 183. Let's take this here. In order to solve it, you basically take x plus 2 and multiply it by itself, which is going to give you x squared plus 4x plus 4. And the reason I know that so quickly is because of the pattern that's associated with this. The pattern that's associated with this allows you not to FOIL it and know that the end result is going to be whatever the A position is squared added to double whatever the product of A times B is. And in this case, the product of A times B was 2x. We doubled it and gave us 4x. And then the final position is B gets squared. That's your end result. That's a perfect square trinomial. The same universe exists if it is a minus q minus 3 squared, for example, is the same thing as taking q minus 3, multiplying it by itself, and the result would be q squared minus 6q plus 9. I know this because of the pattern a minus b squared, the second perfect square trinomial pattern, which when the same thing is simply being multiplied by itself, the result is always going to be whatever a is squared minus double the product of a and b added to b squared. If you don't believe me, FOIL it. Every time you'll be right. Now, a couple of samples of how that might work for us, okay? I'm going to do 2 examples of how knowing this knowledge might work for us. I'm going to kind of start example 2. I'm going to start and stop a little bit. Example 2. Let's just say I say to you h squared plus 6h plus 9, and I want you to factor that. The first question I always want you to ask yourself is there a greatest common factor among all 3 components? These guys share h's, these guys share 3, but nothing is shared other than 1 among all 3. Question number 2, is there a pattern? The first pattern we're learning is perfect squares. Ask yourself, is the first piece a square? Yes, it is. Whose square root is h? Root is h. Is the last piece, that should be a p, a square? The root is 3. So right now I have h and I have 3. If I multiply these 2 pieces together and double them, can I come up with the middle term? In order to do so, what must the sign be? Positive or negative? Positive. Therefore, the factor of this item is h plus 3 squared. Okay, question number 1. Is the first piece a square? Last piece a square. Taking the 2 roots and doubling their product, if it gives you the center component, You have just identified your factor. To test yourself, what can you do to verify that this indeed creates that? Yeah, multiply it. Very good. And go back to what you know about squaring, right? A plus B squared, a squared plus 2ab, okay, plus b squared. Okay, so this is what they're going to give you, and they're going to ask you to factor it. Let's try another one, and we're going to do the other perfect square trinomial, which will give you in subtraction form. Okay, what if I give you this? Z squared minus 12z plus 36. Okay, what's the first question you're going to ask yourself? Before that, before we go there, before we go to patterns, greatest common factor. Is there anything shared among all three? No. Step 2, patterns. Okay. Perfect square trinomials are my favorite pattern. They're one that you're going to see very, very frequently as we factor. First piece, is it a square? What's its root? Last piece, is it a square? What's its root? If I multiply a by b and double it, can I create the centerpiece? What will the sign have to be in order for that to be true? Very good. Which means this should multiply together to give us that if you answered those questions correctly. Foil it to test yourself, or do your a squared minus 2ab plus b squared and hope that it gives you that. And if it doesn't give you that, then what? Did something wrong, right? I would recommend testing these for a long time before you get real comfortable with them. Okay? That is the first pattern, perfect square trinomials. The second pattern I actually like better, only because it's easier to recognize. I want to check on time really quick, guys. Okay, the second pattern I like better. It's easier to recognize. And that pattern is the difference of squares, bottom of page 183. Okay, so I'm continuing with example 2. A squared minus b squared. This is difference of two perfect squares. You guys saw this before. To create this, you would be multiplying together the same two pieces in a binomial, only separated by a positive and a negative. Okay? So instead of it being the same thing, h plus 3 squared, if it was h plus 3 being used again, it would be h plus 3h minus 3. But let's see what that might look like. Let's say,
Chairman Carpenter to the office, please.
I'm trying to make one up that's not already being used in your book. I said I'm trying to make one up that's not already being used in your book. Hang on here. 4a squared minus 25. Here's a good one. Okay, first question. We're going to factor this. What's the first question every single time? Is there a greatest common factor? Beautiful. Second question is it a perfect square trinomial? How do you know absolutely without a doubt that this is not a perfect square trinomial? Two pieces. Very good. So it's definitely not a tri. It's possible, though, it is a perfect square of some sort. It's a difference of two perfect squares. How do you know that? Subtracting two perfect squares. If that is the case, then the square root of the first term plus the square root of the second term multiplied by the square root of the first term minus the square root of the second term will be your factor. Okay, I know. What's the square root of 2a squared? I mean 4a squared? 2a. That goes in the first position of both of your factors. What's the square root of 25?
Plus 5 and
Yep. And it doesn't matter which one you make plus or minus. It makes no difference. You could do 2a plus 5, 2a minus 5. There is no rule as to which way it has to be. Okay? It makes absolutely no difference. Okay? Or maybe something as simple as this. A squared minus 16. Greatest common factor? No. Perfect square trinomial? No. What will the factors here be, folks? A and 4. And there you have it. Okay? So, perfect square trinomial, difference of squares. The first two items. See, we're looking at a playbook, folks. We're just memorizing the plays. We're memorizing the rules that we can use and how to use them most quickly. Okay? That pretty much summarizes page 183. Now, there's one more pattern. Only one more pattern set, and that's the sum of cubes, which we're going to look at briefly here. Okay? Sum of cubes. Now, we know what squares are. It's anything that has a root. Okay? Anything that has a square root. But we're going to look at cubes now and see what cubes look like. Let me slide down a little bit.
Oh, she's looking at the screen.
Sum of and difference of cubes. So let's look at y cubed plus 27. And by the way, this is going to take the sum of cubes pattern. I chose it special. Okay. Is there a greatest common factor? Is it a perfect square trinomial? Plus or minus? No. Is it a difference of two perfect squares? So see how I'm going down the list? Is this the sum of two perfect cubes? The only way that is true is if both of these has a cube root. What's the cube root of y? I mean, y cubed is y. And what is the cube root of 27? 3. Okay. This is where knowing the rule is the only way that this is going to be efficient. When you have the sum of cubes, the rule is a plus b, in other words, the cube root added to the cube root multiplied by, so let's make it add, that first component squared, y squared, and then minus the product of a multiplied by b. What's a times b? 3y. Subtract it. Added to b squared. 9. Okay? This factor pattern is the sum of cubes. So after asking myself greatest common factor, perfect square trinomials, difference of squares, I get down to sum of cubes. Now sometimes, I'm going to say this right up front, you're going to know right off the bat if you see 4a squared minus 25 that that's a perfect square, difference of two squares. So you're going to start recognizing stuff. Just like you recognize other teams and how they play, you're going to start recognizing these the more you practice them. That was sum of cubes. Difference of cubes. Let's see. Let me find a difference of cubes here. Difference of cubes. They don't give me all the examples that I wish they did. I'm just going to use their difference of cubes example, okay? So this is example 3, by the way. Sum of cubes, difference of cubes. I'm going to give you their example. Just, no, that's not a difference of cubes. Hold on. This one. Y cubed minus 1. Okay, it doesn't have a greatest common factor. It's not a perfect square, a difference of squares, but it is a difference of cubes. Difference of cubes. Difference of cubes takes the pattern a minus b, so square root minus square root, multiplied by a squared plus ab plus b squared. By the way, I still have to look. For whatever reason, I have a mental block with memorizing these. Try to memorize them if you can. What's the square or the cube root of y cubed? Minus the cube root of 1. Okay, we're just filling it in now. Now we have our pattern because we recognize it's a difference of cubes, but we're gonna just fill them in. Okay, y squared plus, yep, that's it. By knowing the pattern that fits with a cubed minus b, that should be a 3, a cubed minus b cubed, we are able to obtain the following factors. Okay? Now sometimes, I'm sorry, that was actually example 4. Geez, I skipped example 3, but there's a reason why. That was actually example 4. Sum of and difference of cubes. Now the reason I skipped it is because in example 3, you find that sometimes you will first pull out a greatest common factor and then see that there's still a pattern and you're not completely done. You're only done when the entire thing is prime to each other. In other words, doesn't share anything or doesn't have any patterns. Let's take, for example, here's the one I'm going to do with you. 2u to the 4th plus 54u. 54u. Okay, does it share anything? What can we pull out? 2u, right? Which leaves me with u cubed. What's 54 cut in half? Plus 27. Okay, don't think you're done. You just greatest common factored this mess. Is there anything else that can be done with this? Does it match any patterns?
Yeah.
It's what? Sum of cubes. So first we found GCF, and now we have discovered that what we're left with is sum of cubes. Okay, 2u is going to reside in the final answer along with the factors of this after we've sum of cubed it. So sum of cubes is a plus b, a squared minus ab plus b squared, which is square root plus square root. So that would be u plus what? Cube root plus cube root. 3. What's u squared? U squared. 3 times u subtracted? B squared. Therefore, this entire phrase is the factored incompletion version of that. Now the thing is, a lot of you will quit right here and not keep asking yourself the question. You know you're done when each component shares nothing that can be pulled out or has no patterns left to follow. Like what I would do right now is I would say, okay, wait a minute, this might be a perfect square. Square root of this is u, right? Square root of that is 3. If I multiply these together and double them, do I get that? No. Which means it is not a perfect square. Which means you're done right here. But you do keep asking yourself that question. Okay? You definitely do keep asking yourself that question. All right, in the interest of sanity, man, there is a lot here today. I am actually going to stop and have you guys only go up to number 20. And do add up to 20.